Welcome back, everybody. Today we're going to pick up where we left off last time, which was when we discussed that there's many types of logic. We use them for many different purposes, and some of your training today will have you divide into different subjects. For example, we saw that one of the ways we reason is with classical logic. Classical logic will be used very often in the sciences. It's a good assumption that most of the people around you will be able to discuss classical logic. It's the one that feels the most complete and understandable. It has notions of true and false, and we leave it right there. So this will be good when you want to have very concrete, no holes in the argument type reasoning. However, it's somehow too strict for many other applications, and it's important to know that as you move along in your applications, you need to have a broader view of logics. Some non-classical logics include intuitionistic logic. This is where you can only reason from evidence. So we don't have truth from some other sources, we have to have some data backing it up. This is important when you program because machines can only pick up from the data they have. So if they lack data, they can't produce the same conclusions that you might create from your other understanding and intuitions. So intuitionistic logic is a good match for trying to match what you're doing in computations, programming, and so forth. Another non-classical example are the paraconsistent logics. These are examples where we try to keep to true and false as much as possible, but sometimes we find ourselves in a gray area, a place where the best thing to do is to assume that there are ways in which it is both true and false. There are other forms of this, including fuzzy logic and modal logic, but the key idea is to know and recognize that many situations with real concrete data and information will require you to have a more nuanced notion where we have some notion of true and false together, and it doesn't defeat reasoning. Other things that we won't talk about, but that you might find useful as you move on, are things like modal logic. This is when you want to argue about what's possibly true versus what's necessarily true. Many times the situation is very subtle, and you can argue with other logics like classical logic and probability, but even so, it's important to know that many models like modal logic exist, and then there are others like linear logic which help you argue about resources. It's one thing to know something exists, it's another thing to be able to use it. Maybe a commodity has to be shared amongst individuals. So then, while there is one broom, if two people have to use it at the same time, that's not possible anymore. So resource sharing is an important piece of logic as well. Just be on the lookout for the logic that matches your situation the best. Remember, you will be receiving this as a story problem and returning that to a situation. But today's lesson isn't about what types of logics, it's about how do we tell each other what logic we have. And this is understood through the concepts of context. So let's take a look at what context could mean. In a simple example, we might have a game of a sport. We could ask a true-false question. If the player steps on the line with the ball, do they forfeit the ball to the other team? If you know the rules of basketball, you would conclude one thing, but it would be different if you were to know the rules of, say, soccer. In basketball, stepping on the line forfeits play. It's considered out of bounds to be on the line. And in soccer, on the other hand, you can still be on the line and be considered in. The rules, of course, matter to the context. We'd have to know what we're doing in order to be able to answer honestly whether it's true or false. This is the nature of context everywhere. And just like knowing the rules in the sport matters, it needs to be said in our programming and our reasoning. So let's take a look at what this looks like in the two different contexts that we'll explore. I'll lump these into two categories, though they're not always separated quite so clearly. But I'll talk about the programs, and I'll talk about the sciences. Programs are often very good at explaining their context. The most important context you might see in a program starts at the top of a programming file, most of the time. It's with words like import, or using, or including, other keywords like this. The syntax will change from one programming language to another, but the rules are that we're trying to tell everybody who's reading our code, as well as the computer, what assumptions we're willing to make about what will follow. Oftentimes this includes all kinds of data structures, maybe some files that are accessible to and from the program, as well as any kind of rules of how they should interact with each other. There can also be statements that at the top turn on and off based on the situations in which you're in. These are known as the explicit context. The word explicit here just means that you can see them. They're part of the description of what you're doing in your program, and they're made very clear. Mathematics is less explicit, but there are examples where, when we need to explain it, we'll either add in words or symbols, something to denote that we are talking about mathematics one way versus another way. So take, for example, the natural numbers. These are the numbers you learn to count with. 1, 2, 3, 4, with a number like 0 to reset the counting. Whether you think of 0 as a natural number or just a reset is really up to you. People differ on this position. The net result, however, is that we have notions like 2s and 3s and 5s, and we have a notion of addition with these numbers. So in the context of natural numbers, 2 plus 3 equals 5, we can judge that to be true. To indicate this, we use this special symbol. It's called a turnstile. This symbol here, I've highlighted in blue, it looks like a letter T on its side. It's actually the combination of two symbols. One is to declare and one is to prove. These two symbols together tell us that we're trying to say that the natural numbers declare something and they also confirm it. So here we're saying that natural numbers together with all the rules about natural numbers and counting would lead us to conclude that 2 plus 3 equals 5. Now let's change this. Suppose that we weren't interested in the actual numbers 2 and 3, but we were interested in what's known as their parity. That is it an even number or an odd number? We could change that context and still have a different equation. For example, the notation for parity in mathematics is to use the letter Z and put a little sub 2. The 2 here indicates mod 2, and it indicates whether there is an even or odd number. Zeros will be evens, ones will be odds. Once we put Z mod 2, that notation, then we put the turnstile, that sideways T. We're telling everybody to read the following equation in this new context. So we would say, is 2 plus 3 the same as 1? As natural numbers, that would be definitely false. However, if we think of it as 2 is even, plus 3 is odd, is an even plus an odd the same as an odd number? Yes, it is. So this becomes true in the context of parity. It's really important that you see that context not only changes what logic we might have, it changes what claims might be true. This is the whole role of context, to clarify what we wanted to say. When we go forward, if we need to make an explicit context, we often use it with symbols and words. An abbreviation that will be very common is CTX, or the letter gamma. Mathematicians like to use a single letter. They reduce it to gamma very often, but there's nothing wrong with writing a whole word out there or using a sentence in the context of, and then fill in the blank. Now there are a few catches. Many things are so common that they are a bit technical and boring to repeat every single time. When this happens, we move to something called implicit context. Implicit context appears both in programs and in mathematics, and is the most likely place that you'll get most of your facts in math. So, in a program, some of the implicit contexts come from the operating system. One operating system may behave with certain rules that another one doesn't. There's also something called a runtime. This is what your program is actually running inside of when you create it, and that changes based on the programming language and many other subtle features. And then there is also the hardware. What is this chipset going to do? Does it allow certain kinds of computations or different kinds of computations? That affects the meaning of everything as well. And then there are industry standards. If somebody says, I want to represent an integer or a decimal number, how many digits of precision are they allowing? There are industry standards to help guide that. But once we know their standards, we don't have to repeat them every time. We assume everybody is using the common standard. And so we simply have to tell everybody, use this common standard, and then that brings in implicit information. In the mathematics world, implicit language comes from the books, the courses we're in. Are we in a math class, in a data science class, in a computer science class, in a physics class? Each one of those are clues as to the context. And the titles of books can often show it. Many books have a series. They'll have a title at the top that tells you the context. Here I've displayed a book that says Graduate Text in Mathematics. It's already assumed that the reader has, from context, undergraduate mathematical background. Then it further narrows it by saying the title of the topic. All of these are clues about implicit context. You can't always understand quite precisely what something means, but these implicit and explicit contexts help us frame what logic will mean. And without expressing these, we can often run ourselves into circles. Whenever you're in doubt, move the implicit context into explicit by declaring what references you're using and what context you'd like to discuss. That way we avoid confusion. Let me give a demonstration of where context that's implicit can lead to some serious differences. On the one side, I have a program, and on the other side, I have the equivalent mathematics. Let's go through the mathematics first, and then we'll explore the program. In my mathematics, first I've set the variable x to be the square root of 2. Then I've created y as 30 times x. Then I subtract 29x from y. Well, what should happen here? Well, y is 30x, and minus 29x should leave us with a single x. And a single x is the square root of 2. Now let's go back to the program and check what's happening. If we look at the square root of 2, we see that the computer has created a decimal approximation of 2. It's the best thing it knows how to do. That's based on the context rules. Now there are actually programming languages that do something different. They do what's called symbolic computation. It looks more like the math. You would have to change the context. Here I'm in a context where it's doing decimal approximations. It's an implicit assumption. I didn't make that choice, the computer made it for me. But it has consequences to what we do. When we take 30 times x, we get another decimal approximation, and there's some rounding errors. And once we take away 29x, the rounding errors compound, to the point that once we compare it to our original number, 30x minus 29x no longer equals x. They're off by many decimal places. You can see that the first few digits are the same, 1.414, but by the time we get down to the last two digits, we're off. This is an important lesson to remember when you're doing computations. You'll have approximations, so you'll have to think, how close are they? Are they close enough? Well, these two differ in very small digits, but they aren't technically equal. So this is where context can really change the calculations. Once you've done a little bit of context, here's what we want to do to take away. Implicit context are all the things that we have to assume in the background. We assume typically the common things. We don't want everybody to have to work through and read pages and pages just to get started. Use the implicit context in things like homeworks and discussions with other scientists. You want to be thinking about, why is this true for everybody? Whenever in doubt, pass that to your explicit context with key words like import and include. It's very clear that they're explicit. In mathematical symbols, you can use that turnstile, or you can just write words. Whichever way you do it, please be on your toes about context. Often, a misleading example is based on starting from different contexts. Until next time.